Now let's come to these two vertical segments of the rectangular loop and calculate the forces as well as the directions of the forces acting on these two length segments. Now if you look at this segment, it has a length small a. The current flowing in this loop is in the downward direction and it is I. The field in which it is placed is B, and let phi be the angle between A and B. Now what about the angle between this small a and capital B? It is 90 degree. So if you put sine of 90 over here, it will give us IAB. I is the current flowing, A is the length of these two parallel sides which are vertical, B is the magnetic field in which this loop is placed. So this is the force on this side 1, and what would be the direction of this force acting on this segment of the loop if you apply the Fleming's left hand rule by stretching the first finger of your left hand in the direction of B, and current is flowing down, so your middle finger should point down. Then the stretched thumb will be pointing towards you or out of the page. So this is the direction of the force on this segment A, which is having length A. So F1 is equal to IAB, directed out of the page. Now what about the other parallel side which is having the same length A but carrying a current in the opposite direction? So it is directed upward. Here the current was downward, and since it is flowing it is flowing clockwise, so in this segment it will be moving up. The angle between B and A is again 90 degree. So the magnitude of the force will still be IAB. Sine of 90 is 1, so F3 is also equal to IAB. But what about the direction of the force acting on this loop? Again, using the Fleming's left hand rule, stretch the first finger of your left hand in this direction, that is the direction of B, and your middle finger should point up in the direction of the current. So the thumb will be directed inwards or into the page, which is indicating the force on this particular segment of the loop. So here the force is inwards, here the force is outwards. So this will be pushed forward, this segment will be pushed forward, this will be pushed backward, and in this way there will be a clockwise turning effect produced in this loop. So this rectangular loop carrying the current I and placed in the magnetic field B will turn counterclockwise about this z-axis. This is the axis of rotation for this current loop. So here you can see in equation number 31 and 32 of your book, these two are showing the magnitudes of the forces acting on the side 2 and 4, which were the longer sides of the rectangular loop, and it's the length of these two sides was equal to b, small b. This was the angle 90 minus theta between B and capital B for the side 2, and this 90 plus theta is the angle between the side B and capital B for the side 4 of the rectangular loop. Now 90 minus theta and 90 plus theta both are equal because of theta. So here you can see that the forces F2 and F4 on the side 2 and side 4, the longer sides of the rectangular loop having length b is the same and their directions are opposite, so they cancel out, and these two forces contribute nothing to the torque acting on this current loop. Now to repeat once again, the forces acting on F1 and the forces acting on the side 1 and side 3, that is F1 and F3, they are equal and opposite, but their line of action is not the same, so they do not cancel and they form a couple, which causes the loop to rotate about the z-axis. So these are the forces which are responsible for producing torque in this rectangular loop, which is carrying current I and is placed in the magnetic field B. Now let's calculate the torque which is acting on this current loop. So the formula of the torque is, if you remember, this is equal to let me just the torque is indicated by the symbol torque, and it is equal to the torque is equal to R into the force into the sine of the angle theta. But here the angle is not theta, it is phi. Okay, so we will write it as phi this is not a proper way, but anyway, you should keep it in mind that this phi is the angle between R and F. So what is this R? This is the moment arm. Okay, and the moment arm is the perpendicular distance between the axis of rotation, which in this case is this z-axis, and the point of application of force, and we are considering the forces on these two vertical sides. So what is R in this case? Let me show it to you. This would be R. This is small r. Small r is the distance between this axis of rotation, perpendicular distance between the axis of rotation and the point of application of force. Force is applied here, so this distance is the moment arm R, which is shown in this figure. The force here is F1, and the sine of the angle phi is the angle between R and F. So here you can see F is perpendicular to this line segment, this is also perpendicular, so the angle between the two is 90 degree. That is, the angle between R and F is 90. So we are left with tau equal to R and F. This is actually F1, and F1, if you remember, now what is this R? This whole side has a length equal to B. The length of this whole side is B, so this much distance is B by 2. This much distance is B by 2, so R will be equal to B divided by 2. This will be equal to small b divided by 2. And what about this F1? We have just calculated it as I into A, the length of this side, and this is I into